Okay, so today we're going to work on an example mass balance problem. Um, so problem is that air is pumped through a tank of liquid hexane at 0.25 millimole per minute. The exit stream has a mole fraction of zero point 0.2 hexane. Calculate the time required to evaporate 50 meters cubed of hexane. So we're calculating a time. So we have here like a batch process, and we're going to be doing, um, an integral mass balance because we have accumulation now, or, depletion of hexane in this tank. So the first step, right, is we will draw out our diagram. We have this inlet stream that is just air, and that is at 0.25 kilomole per min. And then out here, so I'll also draw this like we have hexane in here, and then like the air goes through and it's evaporating the hexane. Um, so here we don't know what the flow rate out is, but we know that we have 0.2 hexane. And that means that the remaining fraction must be 0.8, um, fraction of zero point 0.8 air. So, and then here, this is, I guess I'll just put 1.0 air. We know this. Okay. So we need to figure out, um, I guess, how much hexane is leaving, what the rate of hexane leaving is. Um, and Yeah, and once we have that rate, we can calculate how much time it'll take to evaporate a certain amount of volume. Um, so to get the rate of hexane leaving, right, if we have this flow rate out, we know that we have zero point 0.2, 20% of this outlet stream is hexane. So we need to find uh, that flow rate out. How can we can, you might be able to see that we can do that pretty easily with an air balance. So I'm gonna copy our equation here. Okay, so for air, um, we have air going in, we have air going out. It's not generated or consumed. And then I guess we have an assumption here that like the air is not dissolving in the hexane. So we can say that like the air is insoluble um, in hexane. That might be given to you by your teacher, but that's kind of an assumption that we're making here. And then, because it's not soluble, all the air goes in, comes out. We have no accumulation. That's zero. So it's at steady state. So we have a simple in equals out. Well, what's going in? We have 0.25 kilomole per minute. And then if I scroll up, what's coming out? Well, we have N out times the mole fraction of air. So we'll go back down here. We can write that as 0.8 times N out. And then solving for N out, we will get 0.31, that's bad, 33125 kilomole per minute. Okay, so now we're ready to um, figure out what the rate of hexane leaving is. So for hexane, um, we know that it's going to be 20% of this N out, right? Box this. So ooh, pretty easy. We can just say N out for hexane. So the rate hexane is leaving is then going to be, let's see, zero point 0.2 times N out, 0.3125 is 0.62, oops, 0.0625 kilomole per minute. Okay. And so now we're pretty much ready to solve for the amount of time, right? I mean, you can just kind of reason through how to set this up and solve for it, but I'm going to note that it is what's called an integral balance. So an integral balance, that's what we're doing here with this time term. Um, so I will bring down our general mass balance equation. And I'll just show you how this is like what's going on behind the scenes. Um, so here we have no in term. There's no generation, there's no consumption because we have no reactions, but we do have an accumulation term. But like again, it's not really accumulating, it's more of like depletion, but still it's like how the mass of the system is changing with time. So we can, then write this as like N out, right? Is then equal to the accumulation, which, well, you can think of this as dn. And this is for hexane specifically. Like we could put a little hexane um, notation there along with out. So it's like hexane out. Um, so yeah, then like, you just do your standard like separation, integration. And this would be dt and then dn. And then here we have from the initial to the final and over here from time 0 to some time t. And then if you solve this, you're going to get an out times t. And then here you'd have like your n final, which we can take as 0 because we're just trying to figure out how much time it remove 50 meters cubed minus ni. And then this, that's really going to be like our density, the density of the hexane, or like specific gravity rather, times the volume we're curious about, times the molecular weight of the uh, of hexane. Um, so that's like really what's going on here, but you don't need to do any of that. I wouldn't. I would just think, okay, we have, this rate here of hexane out. Um, and then we need to remove 50 meters cubed. So we can write this as, so we're going to have 0.0625. Let me see if I can fix that. 625 kilomoles per minute times some amount of time that we're solving for. And that's going to be equal to, we're trying to remove, I'll write the units on this side because we're going to have to do some conversions, 50 meters cubed. And then, let's see if I have this right. I think that is, yeah, 10 to the third liters per meter cubed. I think, is that right? I think so. Um, and then, okay, so that gets us to liters. And then I have here, you can just look this up. The specific gravity for hexane is 0.659. And that's going to be kilogram per liter. And then finally times the molecular weight. So we can get this kilograms to moles. That should be, we're going to have 86.2 kilogram per kilomole. Okay, and then I'm just going to simplify this right side. Pull up my calculator. That is 50 times 10 to the third times 0.659 divided by 86.2. I get 382. 382.25. I'm just going to round that to 3. Don't check my sig figs here. I haven't paid attention to that. And that's K moles. And then on the left side, see if I can move this over a little bit. We have time and then 0.0625 K mole per minute. And then we can divide our 382.3, 382.3 divided by 0.0625 is the time required is equal to 611, fix that one, 6116.8 minutes. Which is equal to 100, about 102 hours, roughly. So there's our final answer. Now remember, this was called, and what we did here for hexane was an integral balance because it was it's kind of like a batch process that we were talking about here, at least in the terms of hexane. We had an accumulation term. We were solving for time. And I mentioned that like in the background, this is kind of what was going on here, where we had our accumulation term, which changes your accumulation or depletion, changes with time, the amount of hexane in the system. So really in the background, you're doing this integration. I don't think your teacher is going to make you show that. Maybe they will. I would just jump straight to the balance that we did and kind of like reason through it in my head. And then I guess I should also know, I don't know if I did that what we did for the air, this is just called a differential balance because we just have like, we didn't have accumulation term. That was zero right there, right? So there was no like integration done, and we just have these rates, like the rate in, the rate out. So that's called what we did for air is differential balance. What we did for hexane is an integral balance. Um, and yeah, I mean, pretty simple problem. I hope that, this kind of helps you see like the differences between the types of mass balances you may do, differential versus integral. Pretty simple. I'll make another video or a couple more with maybe some more challenging problems where we have like multiple unit operations, mixing streams, um, things like that. So we'll see what comes next. Hope this was helpful. See ya.